Okay, so for some reason that other video cut off, so my apologies. So we're going to continue. All right, so let's go back a little bit. So I'll still try to keep it under what I said, 20 minutes. So we went from f sub n minus 1 plus f sub n minus 2 is less than or equal to alpha to the n minus 2 plus alpha to the n minus 3. Now here, it takes some more, like I said, these proofs now are becoming more and more intuitive as we learn techniques. As we're really mastering these techniques, the proofs are becoming more and more intuitive, more and more sophisticated. So here we have, so hopefully from these two steps, you guys are clear. Now from here to here, it takes a little bit of thinking, but you always have to go back to see what they gave you in terms of what you suppose or what they gave you initially, and to see if you use that anywhere in your proof. If you didn't use that in your proof and you get stuck, then you need to find a way to use it. So if we go back to the very first page, we were given something, right? We were given this fact right here, and that we haven't talked about. So we said let alpha be the positive solution to the equation x squared equals x plus 1. So in other words, this is what this is saying. This is saying that since alpha is a solution, then alpha squared equals alpha plus 1. Okay, that's what it means. It's a solution to that equation. Okay, so now let's go back. So here we have alpha, and so now what I'm doing on this line is finding a way to get an alpha squared. So that's why I'm rewriting this right here as alpha to the n minus 3 plus 1, because I know when I factor out that alpha n minus 3, I'm going to get something squared. So let's see. So this becomes alpha to the n minus 3 times alpha plus 1. Okay. And since alpha is a solution to x squared equals x plus 1, that means, like I said before, alpha squared equals alpha plus 1. So we can rewrite this by substitution as alpha squared. Okay. And if we simplify that, right, because these are the same bases, if we simplify that, that gives us alpha to the n minus 1. Okay. And so therefore, f sub n is less than or equal to alpha to the n minus 1, and therefore, no, I guess I could have said thus. And so therefore, by the PCI, f sub n is less than or equal to alpha to the n minus 1 for all n greater than or equal to 1. This definitely deserves a QED. Okay, so I'm actually going to discuss the well ordering principle. We're going to look at an example, and then we'll be done with the notes. And in section 2.5, keep in mind, if anything is unclear, you should always go to the book or look at other resources to see if you can clarify some things. Okay, and so the well ordering principle, again, you might want to stop the video, write this down, and then resume the video. Okay, so it says every non-empty subset of n has a smallest element. That's what the well ordering principle tells us. Every non-empty subset of n has the smallest element. And there's generally a structure, not as formally as the if then conditions or quantifiers or things like that, but there's usually an overall approach, or a general approach, I should say, to applying or using the well ordering principle in your proof, for a proof actually. Okay. And so here the structure is, well, so the well ordering principle again, and again, we're talking about natural numbers. So when you're talking about natural numbers, you usually deal with induction, or now we can do the well ordering principle. And so every non-empty subset of naturals has the smallest element. Okay. All right, the structure is, one, you assume a certain property. So it's sort of this approach by contradiction if you use the well ordering principle. So assume a certain property does not hold for n. Well, if that's the case, then this is going to produce a non-empty set of natural numbers that doesn't have that property. So not having the property. And usually your contradiction comes in by exploring that smallest element in that set. Okay. Okay, So now we're actually going to go back to the proof that we proved in class using induction. This time we're going to use the well ordering principle in terms of our proof. Okay, so prove that and the well ordering principle, that's a fact that's given to us. I think it might have been brought up earlier in the course, but this is a fact given to us that every non-empty subset of the naturals has the smallest element. So that's been given to us. So in terms of our proof, we're using that fact in this type of proof. Okay. So I just want to be clear on that because that's something, once we know we have a non-empty subset of the naturals, then we know there has to be a smallest element because that's what this principle tells us. Okay, I just want to make sure we're clear on that. Okay, so the proof of this, well, again, similar to like what we did before, I guess I want to be consistent. So let n belong to the naturals and n is greater than 1. All right, so if n is prime, then n is a prime factor of n, right? Okay, so we're done with that case. If n is composite, then n has factors other than 1 and n. Okay, so what does that lead, or what can we say then? Well, therefore, if this is the case, the set, so we can create a set T such that m belongs to the natural because we need to state another variable, and m divides n because that's what it means in terms of being a factor. So m divides n. However, m doesn't equal n, and m, what else? Cannot equal 1. Okay. So therefore, the set T is a non-empty, because if we're assuming that it's composite and we're assuming that n has factors other than itself and 1, then this set right here, T, is a non-empty. So basically in this, when you're doing a proof with this approach, you have to create this, you have to show that this non-empty set exists in order to use the well ordering principle. But the fact, again, because we said it was composite and things of that nature, we create this set T and we know it's a non-empty subset of the naturals. So therefore and I'm using shorthand so you can write it actually out long way, but by the well ordering principle, T has the smallest element, and let's call that element P. Okay. So now let's think about this. What are we trying to show? Because I know, like, okay, where are we going with this? Well, we're trying to show that n has a prime factor when it's, no matter if it's prime or composite. We showed that when it's prime, it has a prime factor. So we're done with that. Now we're saying, okay, let n be composite, that n has factors other than 1 and n. So therefore, there's a set T, and I'm just reiterating, there's a set T such that m is part of the naturals, such that the set equals m is part of the naturals and m divides n because m is a factor of n, but m does not equal n and m is not equal to 1. So we're saying we're saying that it's composite, right? Okay. So now let's go back here. And so by the well ordering principle, T has the smallest element, call it P. Well, what we're really trying to show from this point is that we need to show what? That P is prime. Okay. Well, since we're trying to show that P is prime, let's suppose P is composite. Okay. So if we suppose P is composite, then, and I think I'm almost run out of time. So we're almost done with this proof, so that's good. Suppose P is composite, then P, right? If P is composite, then P has a divisor. Let's call that divisor D, where with D can't equal P, right? And what? D can't equal 1. Okay. Well, if this is the case, since D divides P and P divides N, so this is where all those past theorems and things, and I was talking to someone about, you have to remember all those other theorems we proved to help us in future proofs. So you really have to keep that in mind. So since D divides P and P divides N, what can we say? D also divides N. Okay. D divides N. Well, if that's the case, then we can say, therefore, what? What do we know then? Well, D also is in T, right? Okay. However, so hopefully you're seeing this contradiction now, but this is a contradiction since if we're calling D a divisor of P and D is not equal to 1, so D is less than P, since D is less than P, and P is the smallest element of T. Okay, so therefore, P is a prime factor of N. Okay, so I am actually, so that's the end of the notes. What I will say is this, because in your book, there are some proofs that I want you to look at. So look at the proof in the book. So in your book, look at the proof and see if you can understand it. So don't just look at it to be reading it to say you've read it, but actually see if you can follow along in the steps. And a lot of times when the book do proofs, they leave out steps because they're, it's more sophisticated, saving space. So any steps that's left out, see if you can fill in those steps. So the one in the book that says for every n belonging to the naturals, so every natural number, n plus 1 equals 1 plus n. And I know you're saying, well, its addition is commutative. We already know that. But in the book, they're actually saying, well, let's assume addition isn't commutative. Okay, because when you guys, for those who's taking abstract algebra, you're going to get to a level where stuff isn't, you can't assume those properties depending upon what universe you're in or what domain you're in. But that's outside of this class for the most part. So look in the book at that proof and also look at how they prove, or I should say prove, not proof. So look at this one and look at the division algorithm. And then also sort of just look at it, but just know when they talk about that so they sort of conclude that the PMI and the PCI are equivalent. So just kind of glance over that. That one is, I think, a little more involved when they do the proof of that. But I just want you to take a look at that. And also that the Will ordering principle is equivalent to the PMI. Okay. And I am stopping here. So see you all tomorrow.